Hello, my name is Yunqian. I am a PhD student at the University of California, Santa Cruz, Computer Vision Lab. Today I'm presenting our paper, POMS Plus, Modular Image-Based Floor Plan Localization, Leveraging Depth Foundation Model. POMS Plus is an image-based localization system for large indoor spaces requiring only a floor plan and a camera. Our goal is to determine the user's location and orientation within an unvisited indoor space. Targeted indoor spaces are usually large, can contain repetitive structures, and are GPS denied. Some examples would be a mall, hospital, or school buildings. In our previous work, we aimed to tackle this problem using the LiDAR sensor on an iPhone to capture local geometry and compare it to the floor plan. From a single stationary scan, POMS is able to estimate possible user locations, but pinpointing the user is difficult in buildings with repetitive structures. In POMS Plus, we extend this work by replacing the LiDAR sensor with a monocular depth estimation models, or MDEs, like the Depth Pro model and the state-of-the-art Pixel Perfect Depth model. By doing so, we allow POMS Plus to see further away using only a camera. This helps with dealing with structural similarities in such indoor spaces. The POMS Plus framework consists of an observation module and a layout matching module. In the observation module, the user would first take one or more images with overlaps from a horizontal scan. We also estimate the camera poses and record the intrinsics. A modular depth estimation model then estimate a depth for each of these images. The depth maps would then be back projected into individual point clouds, very much like pieces of puzzles. However, because monocular depth estimation is an ill-posed problem, although the pieces may have accurate geometry, they usually need to be corrected by scale. To solve this issue, we first find a piece with the largest ground plane and rescale it using a known camera height. We then rescale the other pieces iteratively. For the neighboring frame, we first create point correspondences using their overlapping pixels. Then, we estimate at scale to minimize the total point distances. In practice, we usually jointly optimize the scale for all frames, producing a scale-aligned final point cloud. We then take a horizontal slice of this point cloud and convert it into two convolution kernels. One checks for wall alignment, and the other applies visibility constraints. By convolving the kernels with the floor plan, we get a posterior probability distribution over the pixel space. To account for unknown orientation, we first use a separate module to produce orientation candidates. Then we rotate the kernels with the orientation candidates and repeat the convolution process. Optionally, we also rescale the kernels to be more robust to scale inaccuracies, and we then remove the scale dimension by taking the max at each location and orientation. A direct localization is done by simply taking the arcmax of the resulting heat maps. Let's see this in action. Benefited from the long visibility range, POMS Plus can better tackle structural similarities in buildings, yielding a more concentrated posterior distributions for direct localization. We compared with our prior work and the state-of-the-art model at the time, FCubeLock. POMS Plus shows strong performance in removing ambiguity, as seen here. To further remove ambiguity, we can also perform sequential localization with POMS Plus. As in our prior work, we initialize a particle filter using the resulting distribution and drive the particles using odometry data. After a short walk, POMS Plus successfully localizes the user and tracks them accurately. In addition, we compare our kernel-based layout matching method with FCubeLock's ray tracing-based localization method by sampling oracle or perfect observations from the floor plan. From the oracle observations, we estimate the user location using each method. On the right column, we can see the kernel-based layout matching method produce much better results. Thank you for watching this video. If you're interested in learning more details, try out our code, or use our dataset, please visit our project website or scan this QR code.